हेलो फ्रेंड, तो स्टार्ट करते हैं 11th क्लास की केमिस्ट्री, जिसमें है यूनिट 2 स्ट्रक्चर ऑफ एटम। जिसमें कुछ ऑब्जेक्टिव्स हैं और यहाँ पर एक डेफिनेशन दी हुई है। द रिच डाइवर्सिटी ऑफ, कुछ इंपॉर्टेंट पॉइंट दिए हुए हैं। द रिच डाइवर्सिटी ऑफ केमिकल बिहेवियर ऑफ डिफरेंट एलिमेंट्स कैन बी ट्रेस्ड टू द डिफरेंसेस इन द इंटरनल स्ट्रक्चर ऑफ एटम ऑफ दिस एलिमेंट्स. The existence of atoms has been proposed since the time of early Indian and Greek philosophers 400 BC, who were of the view that atoms are the fundamental building blocks of matter. According to them, the continued subdivisions of matter would ultimately yield atoms which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were mere speculations, and there was no way to test them. Experimentally, these ideas remained dormant for a very long time and were revived again by scientists in the 19th century. The atomic theory of matter was first proposed on the firm scientific basis by John Dalton, a British school teacher in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle of matter, Unit 1. Dalton's atomic theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportion very successfully. However, failed to explain the results of many experiments. For example, it was known that substances like glass or ebonite, when rubbed with silk or fur, get electrically charged. In this unit, we start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. This established that atoms are made or subatomic particles, that is electrons, protons, and neutrons. A concept very different from that of Dalton. Discoveries of subatomic particles and insight into the structure of atom was obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind her basic rule regarding the behavior of charged particles. Like charges repel each other, and unlike charges attract each other. Discovery of electrons. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occurred at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated certain laws which we will study in class 12. These results suggested the particulate nature of electricity. In mid 1850s, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. It is depicted in figure 2.1. A cathode ray tube is made of glass containing two thin pieces of metal called electrodes sealed in it. The electrical discharge through the gases could be observed only at very low pressures and at very high voltages. The pressure of different gases could be adjusted by evacuation of the glass tubes. When sufficiently high voltage is applied across the electrodes, current starts flowing through the stream of particles moving in the tube from the negative electrode cathode to the positive electrode anode. There was called cathode rays and or cathode rays of cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating at the tube behind anode with phosphorescent material zinc sulfide. When these rays, after passing through anode, strike the zinc sulfide coating, a bright spot is developed on the coating. Figure 2.1b. The results of these experiments are summarized below. The cathode rays start from cathode and move towards the anode. These rays themselves are not visible, but their behavior can be observed with the help of certain kind of materials, fluorescent or phosphorescent, which glow when hit by them. Television picture tubes are cathode ray tubes, and television pictures result due to fluorescence on the television screen coated with certain fluorescent or phosphorescent materials. In the absence of electrical and magnetic field, the rays travel in straight lines. Figure 2.2. In the presence of electrical and magnetic field, the behavior of cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. The characteristics of cathode rays electrons do not depend upon the material of electrodes and the nature of gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituent of all the atoms. Charge to mass ratio of electrons. In 1897, British physicist J. J. Thomson measured the ratio of electrical charge to the mass of electron (ME) by using cathode ray tube and applying electrical and magnetic field perpendicular to each other, as well as to the path of electrons. Figure 2.2. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, the electron strikes the cathode ray tube at point C. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path which is followed in the absence of electric and magnetic field, and they hit the screen or at point B. Thomson argued that the amount of deviation of the particles from their path in the presence of electrical and magnetic field depends upon first the magnitude of the negative charge on the particle. Greater the magnitude of charge on the particle, greater is the interaction with the electric and magnetic field, and thus greater is the deflection. Second, the mass of particle lighter the particle, greater the deflection. Third, the strength of electrical and magnetic field, the deflection of electrons from its original path increases with the increase in the voltage across the electrodes or the strength of the magnetic field. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the value of E by me as E by me is equal to 1.758820 is equal to 10 to the power 11 C per kilogram, where me is the mass of an electron in kilogram and small e is the magnitude of the charge on the electron in coulomb C. Since electrons are negatively charged, the charge on electron is minus small e. Charge on the electron R.A. Millikan 1868 to 1953 devised a method known as oil drop experiment 1916 to 14 to determine the charge on the electrons. He found the charge on the electron to be 1.6 to 10 to the power minus 9 and the column. The present accepted value of electrical charge is minus 1.60 to 1 76 into 10 to the power minus 19 coulomb. And the mass of electron ME was determined by combining these results with Thomson's value of E by small me ratio. Mass of electron is equal to E by small E per me is equal to 1.60 to 176 into 10 to the power minus 19 coulomb 1 upon 1.758820 into 10 to the power 11 coulomb per kilogram is equal to 9.1094 into 10 to the power minus 31 kilogram. Figure 2.2 are the apparatus to determine the charge to the mass ratio of electron. Discovery of protons and neutrons. Electrical discharge carried out in the modified cathode ray tube led to the discovery of canal rays carrying positively charged particles. The characteristics of these positively charged particles are listed below. First, unlike cathode rays, the mass of positively charged particles depends upon the nature of gas present in the cathode ray tube. Now, these are simply the positively charged gaseous ions. The second, the charge to mass ratio of the particles depends on the gas from which they originate. Third, some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. Fourth, the behavior of these particles in the magnetic and electrical field is opposite to that observed for electron or cathode rays. The smallest and lightest positive ion was obtained from hydrogen and was called proton. This positively charged particle was characterized in 1919. Later, the need was felt for the presence of electrically neutral particles as one of the constituent of atom. These particles were discovered by Chadwick 1932 by bombarding a thin sheet of beryllium of by alpha particles when electrically neutral particles having a mass slightly greater than that of protons were emitted. He named these particles as neutrons. Is the important properties of all these fundamental particles are given in table 2.1. Atomic model observations obtained from the experiment mentioned in the previous sections have suggested that Dalton's invisible atom is composed of subatomic particles carrying positive and negative charges. The major problems before the scientists after the discovery of subatomic particles were to account for the stability of atom, to compare the behavior of elements in terms of both physical and chemical properties. Third, to explain the formation of different kinds of molecules by the combination of different atoms. And fourth, to understand the origin and nature of the characteristics of electromagnetic radiation absorbed by emitted by atoms. Different atomic models were proposed to explain the distributions of these charged particles in an atom. Although some of these models were not able to explain the stability of atoms, two of these models, one proposed by J.J. Thomson and the other proposed by Ernst Rutherford, are discussed below. Thomson model of atom. J.J. Thomson is in 1998 proposed that an atom possesses a spherical shape, radius approximately 10 to power minus 10 meter, in which the positive charge is uniformly distributed. The electrons are embedded into it in such a manner as to give the most stable electromagnetic arrangement. Figure 2.4. Many different names are given to this model. For example, plum pudding, resin pudding, or watermelon. This model can be visualized as a pudding or watermelon of positive charge with plums or seeds electrons embedded into it. An important feature of this model is is that the mass of the atom is assumed to be uniformly distributed over the atom. Also, with this model was able to explain the overall neutrality of the atom. Experiments for Thomson, uh, but was not consistent with the results of for later experiments. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. Rutherford's nuclear model of atom. Rutherford and his students Hans Geiger and Ernst Marsden bombarded very thin gold foil with alpha particles. Rutherford's famous alpha particle scattering experiment is represented in figure 2.5. A stream of high energy alpha particles from a radioactive source was directed at a thin foil. thickness of 100 nanometer of gold metal. A thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck the screen, a tiny flash of light was produced at that point. The results of a scattering experiment were quite unexpected. According to Thomson model of atom, the mass of each gold atom in the foil should have been spread events over the entire atom, and alpha particles had through enough energy to pass directly through such a uniform distribution of mass. It was expected that the particles would slow down and change directions only by a small angles as they passed through the foil. It was observed that most of the alpha particles passed through the gold foil unaffected and deflected. Second, a small fraction of the alpha particles was deflected by small angles. Third, a very few alpha particles, -1 in 20,000, bounced back, that is, were deflected by nearly 180 degree. On the basis of observations, Rutherford drew conclusions regarding the structure of atom. First, most of the space in the atom is empty, as most of the alpha particles passed through the foil and deflected. Second, a few positively charged alpha particles were deflected. The deflection must be due to the enormous repulsive force, showing that the positive charge of the atom is not spread throughout the atom as Thomson had presumed. The positive charge had been due to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. Calculations by Rutherford showed that the volume occupied by the nucleus is rigidly small as compared to the total volume of the atom. The radius of the atom is about 10 to the power minus 10 meter, while that of red nucleus is 10 to the power minus 18 meter. One can appreciate this difference in size by a real sign that if cricket's ball represents nucleus, then the radius of atom would be about 5 kilometer. On the basis of above observations and conclusion, Rutherford proposed the nuclear model of atom. According to this model, the positive charge and most of the mass of atom was densely contracted in extremely small region. This very small portion of the atom was nucleus. By Rutherford, the nucleus is surrounded by electrons and more move around the nucleus with the very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system, in which the nucleus plays a very role of sun and the electrons that of revolving planets. Third, electrons and the nucleus are held together by electrostatic forces of attraction. Atomic number and mass number. The presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal to, but opposite to that of electron. The number of protons present in the nucleus is equal to atomic number Z. For example, the number of protons in the hydrogen nucleus is 1. In sodium atom, it is 2, 11. Therefore, their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons, atomic number Z. For example, number of electrons in hydrogen atom and sodium atom are 1 and 11 respectively. Atomic number Z is equal to number of protons in the nucleus of an atom is equal to number of electrons in the neutral atom. While the positive charge of the nucleus is due to protons, the mass of the nucleus due to protons and neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as mass number A of the atom. The mass number of protons Z plus number of neutrons small n. Isobars and isotopes. The composition of any atom can be represented by using the normal element symbol called GX, which with superscript on the left hand side as the atomic mass number, small capital A, and subscript Z on the left hand side as the atomic number, that is X, X, A, and Z. Isobars are are the atoms with the same mass number but different atomic number. For example, carbon 6, 6 14, carbon 7 14. Now, on the other hand, atoms with identical atomic number but different atomic mass number are known as isotopes. In other words, according to between the isotopes, according to equation 2.4, it is evident that difference between the isotopes is due to presence of different number of neutrons present in the nucleus. For example, considering of hydrogen atom, again 99.985% of hydrogen atoms contain only one proton. This isotope is called protium, hydrogen 11. Rest of the percentage of hydrogen atom contains two other isotopes. The one containing one proton and one neutron is called deuterium, D12, 0.15%, and the other one possessing one proton and two neutrons. It is called a tritium. The latter isotope is found in trace amounts of the on the Earth. Other examples of commonly occurring isotopes are carbon atom containing 6, 7, 8 neutrons besides 6 protons. Chlorine atoms containing 18 and 20 neutrons besides 17 protons. Lastly, an important point to mention regarding isotopes is that the chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. The number of neutrons are present in the nucleus have very little effect on the chemical properties of an element. Therefore, all isotopes of a given element show same chemical behavior. Drawbacks of Rutherford model. As you have learnt above, the Rutherford nuclear model of an atom is like a small scale solar system with the nucleus playing the role of the massive sun and the electrons being similar to the lighter planets. When classical mechanics is applied to the solar system, it shows that the planets describe well defined orbits around the sun. The gravitational force between the planets is given by the expression g dot m1 m2 upon r square. When m1 and m2 are masses, smaller is the distance of separation of the masses, and capital G is gravitational constant. The theory can be also calculated precisely. The planetary orbits and the days are in agreement with the experimental measurements, and the similarity between the solar system and nuclear model suggests that electrons should move around the nucleus in well defined orbits. Further, the Coulomb's force kq1 q2 upon r square, where q1 and q2 are charges and smaller is the distance of separation of two charges, and k is the proportionality of constant between the electron and nucleus, is mathematically similar to the gravitational force. However, when a body is moving in an orbit, it undergoes acceleration even if it is moving with the constant speed in an orbit because of changing direction. So an electron in the nuclear model describing planet like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiation. This feature does not exist for planets since they are uncharged. Therefore, an electron in an orbit will emit radiation. The energy carried by radiation comes from electronic motion. The orbit will thus continue to shrink. Calculations show that it should take an electron only 10 to the power minus 8 s and spiral into the nucleus, but this does not happen. Thus, the Rutherford model cannot explain the stability of an atom. If the motion of an electron is described on the basis of the classical mechanics and electromagnetic theory, you may ask that Since the motion of electrons in orbits is leading to the instability of the atom, then why not consider electrons as stationary around the nucleus? If the electrons were stationary, electrostatic attraction between the dense nucleus and the electrons should pull us electrons move towards the nucleus and form the miniature version of Thomson's model of atom. Another serious drawback of the Rutherford model is that it says nothing about distribution of these electrons around the nucleus and the energies of these electrons development, leading to the Bohr's model of atom. Historically, results observed out from the studies of interactions of radiations with matter have provided immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr's model of atom. These were first dual character of the electromagnetic radiation, which means that radiation passes on both wave like the particles like properties, and second experimental results regarding atomic spectra. First, we will discuss about the dual nature of the electromagnetic radiations. Experimental results regarding atomic spectra will be discussed in section 2.4. Wave nature of electromagnetic radiation. In the mid 19th century, physicists is actively studied absorption and emission of radiation by heated objects. These are called thermal radiations. Tried to find out of what the thermal radiation is made. It is now well known the fact that thermal radiations consists of electromagnetic waves of various frequencies or wavelengths. It is based on on a number of modern concepts which were unknown in the mid 19th century. First active study of thermal radiation laws occurred in the 1950s, and the theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed in the early 1870s by James Clerk Maxwell, which was experimentally confirmed later by Heinrich Hertz. Here we will learn some facts about electromagnetic radiations. James Maxwell, 1870, was the first to give us a comprehensive explanation about interaction between the charged bodies and the behavior of electrical and magnetic fields of a microscopic level. He suggested that when electrically charged particles move under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiations. Light is the form of radiation known from early days, and the speculation about its nature dates back to remote ancient times. In earlier days, Newton light was supposed to be made of particles, corpuscles. Now, it was only in the 19th century when wave nature of light was established. Maxwell was again the first of to reveal that light waves are associated with the oscillating electric and magnetic character. Figure 2.6. Although electromagnetic wave motion is complex in nature, we will consider here only a few simple properties. First, the oscillating electric and magnetic fields produced by oscillating and charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. Simplified the picture of electromagnetic wave is shown in figure 2.6. Unlike sound waves or waves produced in water, electromagnetic waves do not require medium and can move in vacuum. It is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength, frequency. These constitute what is called electromagnetic spectrum. Different regions of the spectrum identified by different names. Some examples are a ratio frequency region around 10 to the power 6 hertz, used for broadcasting, microwave region around 10 to the power minus 10 hertz, used for radar, and infrared region around 10 to the power 13 hertz, used for heating, ultraviolet region around 10 to the power 16 hertz, component of sun's radiation. A small portion around 10 to the power 15 hertz is the what is ordinarily called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiation. Fourth, different kinds of units are used to different represent electromagnetic radiation. These radiations are characterized by the properties, namely frequency and wavelength lambda. The SI unit of frequency V is hertz, Z inverse. On the after Heinrich Hertz, it is defined as the number of waves that pass the given point on in 1 second. Wavelength should have the units of wavelength, and as you know that the SI units length of is meter. Since electromagnetic radiation consists of different kinds of waves of such smaller wavelengths, smaller units are used. Figure 2.7 shows various types of electromagnetic radiations which differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiations, regardless of wavelength, travel at the same speed, that is 3 into 10 to the power 8 meters per square meter per second. This is called the speed of light, and is given the symbol c, the frequency v, and wavelength lambda, and the velocity of light c are related to by the equation 2.5. The other commonly used quantity, especially in spectroscopy, is the wave number. V. It is defined as the number of wavelengths per unit length. Its units are reciprocal of wavelengths unit, that is meter square per meter. However, commonly used unit is centimeter per, not SI unit. Particles nature of electromagnetic radiation, Planck's quantum theory. Some of the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could be not be explained with the help of even the electromagnetic theory of 19th century physics, known as electric classical physics. The nature of emission of radiation from hot bodies, black body radiation. Second, ejection of electrons from metal surface when radiation strikes it, a photoelectric effect. Third, variation of heat capacity of solids as a function of temperature. The fourth, line spectra of atoms with special reference to hydrogen. This phenomena indicate that the system can take energy only in discrete amounts. All possible energies cannot be taken up or radiated. It is not worthy that the first concrete explanation for the phenomena of the black body radiation mentioned above was given by Max Planck in 1900. Let us first try to understand this phenomena which is given below. Hot objects emit electromagnetic radiation over a wide range of wavelengths at high temperatures. An appreciable proportion of radiation is in the visible region of the spectrum. As the temperature is a higher proportion of short wavelength blue light is generated. Now, for example, when an iron rod is heated in a furnace, if it first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. This means that red radiation is most intense at the particular temperature, and the blue radiation is more intense at another temperature. This means intensities of radiations of different wavelengths emitted by hot body depend upon its temperature. By late 1800s and 50s, it was known that objects made of different material and kept at different temperatures emit a different amount of radiation. Also, when the surface of an object is irradiated with light, electromagnetic radiation, a part of radiant energy is generally reflected, such as a part of it is observed and a part of it is transmitted, is absorbed, and a part of it is transmitted. As the reason of incomplete absorption is that ordinary objects are, as a rule, imperfect absorbers of radiation. An ideal body which emits and absorbs radiations of all frequencies uniformly is called the black body, and the radiation emitted by such a body is called body exists. Body radiation emitted by such a body is called black body radiation. In practice, no such body exists. Carbon black approximates fairly closely to black body. A good physical approximation to a black body is a cavity with the tiny hole which has no other opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. Black body is also perfect radiator of radiant energy. Furthermore, a black body is in thermal equilibrium with its surroundings. It radiates the same amount of energy per unit area as it absorbs from its surrounding, and any given time the amount of light emitted, intensity of radiation from a black body, and its spatial distribution depends only on its temperature. At a given temperature, the intensity of radiation emitted increases, and with the increase of wavelength reaches the maximum value at a given wavelength, and then starts decreasing with further increase of wavelength as shown in figure 2.8. Also, as the temperature increases, maxima of curve shifts onto short wavelength. Several attempts were made to predict the intensity of radiation as a function of wavelength, but the results of the above experiment could not be explained satisfactorily on the basis of the wave theory of light. Max Planck arrived at a satisfactory relationship by making an assumption that as the absorption and emission of radiation arises from oscillator, that is atoms in the wall of black body, and their frequency of oscillation is changed by interaction with the oscillators of electromagnetic radiation. Planck assumed that radiation could be subdivided into discrete chunks of energy. He suggested that atoms of molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy, capital E, of a quantum of radiation is proportional to its frequency v, and is expressed by equation 2.6. Capital E is equal to h v, the proportional. The proportional constant small h is known as Planck's constant and has the value of 6.626 into 10 to the power minus 34 JS. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of in the radiation from black body as a function of frequency or wavelength or at different temperatures. Quantization has been compared to standing on a staircase. A person can stand on any step of the staircase, but it is not possible for her to stand in between the two steps. The energy can take any one of the waves values from the following set but cannot have taken on any values from between them. Mm, photoelectric effect in 1877, H. Hertz performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example potassium, rubidium, calcium, etc., were exposed to a beam of light as shown in figure 2.9. The phenomena is called photoelectric effect. The results observed in this experiment were the electrons are ejected from the metal surface as soon as the beam of light strikes the surface, that is, there is no time lag between the striking of light the beam and the ejection of electrons from the metal surface. Second, the number of electrons ejected is proportional to the intensity or brightness of light. Third, for each metal, there is a characteristic minimum frequency V naught, also known as threshold frequency, below which photoelectric effect is not observed. At a frequency V is greater than V naught, the ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of the light used. All the above results could not be explained on the basis of laws of classical physics. According to latter, the energy content of the beam of light depends upon the brightness of the light. In other words, the number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. It has been observed that through the number of electrons ejected thus depend on the upon the brightness of light and the kinetic energy of the ejected electrons. Ejected electrons does not, for example, red light V is equal to 4.3 to 4.6 and to 10 to the power 14 hertz for of any brightness intensity. We may shine on a piece of potassium ejected, but as soon as even a very weak yellow light V is equal to 5.1 into 5.2 5.1 to 5.2 into 10 to the power 14 hertz shines sun the potassium metal. The photoelectric effect potassium was observed. The threshold frequency V naught for potassium metal is 5 into 10 to the power 14 hertz. Einstein 1905 was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as the starting point. Shining a beam of light onto a metal surface can therefore be viewed as shooting a beam of particles and for the photons. When photons of sufficient energy strikes an electron in the atom of metal, it transfers its energy and so instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Greater the energy possessed by the photon, greater will be transfer of energy of the electron and greater the kinetic energy of the ejected electron. In other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. Since the striking photon has energy equal to hv, and the minimum energy required to eject the electron is hv naught, also called the work function W naught table 2.2. Then the difference in the energy h nu HVH minus h v naught is transferred as the kinetic energy of the photoelectron following the conservation of energy principle, and the kinetic energy of the ejected electron is given by the equation 2.7 hv is equal to hv naught is plus a half me v square, where m is the mass of electron and v is the velocity of associated with the ejected electron. Lastly, a more intense beam of light consists of large number of photons. Consequently, the number of electrons ejected is also larger as compared to that in an experiment in which A beam of weaker intensity of light is employed. Dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the one hand, it could explain the black body radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known aware behavior of light, which would account for the phenomena of interference and diffraction. The only way of resolve the dilemma was to accept the idea that light possesses both particle and wave-like properties, that is, light has dual behavior depending on the experiment. We find that light behaves either as a wave or as a stream of particles. Whenever radiation interactions with matter, it displays particles like properties of contract to the wave-like properties, interference and indifference, interference and diffraction, which is exhibits when it is exhibits it exhibits when it propagates. Now, this concept was totally aligned to the way of scientists through about matter and radiation, and it took on them a long time to become convinced of its validity. It turns out, as usual, see later that some electron microscope particles like electrons also exhibit this wave particle and quality. Evidence for the contest electronic energy levels, atomic spaces. Structure of atom. Evidence for the quantized electronic energy levels, atomic spectra, emission and absorption spectra, line emission spectra, line spectrum of hydrogen, बोर मॉडल फॉर हाइड्रोजन एटम, ये हम नेक्स्ट वीडियो में देखेंगे. प्लीज़ लाइक शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग. नेक्स्ट पार्ट जल्दी अपलोड किया जाएगा, तो लाइक प्लीज़ सब्सक्राइब कीजिएगा इस चैनल को. थैंक्स फॉर वॉचिंग.